Hello and welcome back. In this video, we'll be talking about continuity of functions of two or more variables. We'll start with just two variables though. So remember, for a function of a single variable, continuity meant that the limit as x, our independent variable, approaches some point A of our function is actually equal to the function's value at that point. This is what continuity means. And remember, this meant three things had to happen. One, that the limit existed. Two, that the function existed at A. And three, that the two were equal to each other. The same is true for functions of two variables, and indeed for functions of as many variables as you like. We want the limit, we want f to be defined at that point. We want the limit to exist at that point, and then finally we need the limit to actually be what the function value is at that point. So let's work an example here. I want to determine all the points at which this function here is continuous. So notice it's piecewise defined, and I do have a nice continuous function here in terms of x and y, except when the bottom is 0. So x squared plus y to the fourth, again, this is the square of two real numbers, equal to 0. So that implies that x equals 0, y equals 0. All right, this implies that x equals 0 and y equals 0. And so this guy is going to be continuous, except maybe, possibly, at the origin, right? That's the point where we've taken that piece and we've defined the function to be 0 there. So we know one f of 0, 0, by how our function is defined, is 0. And so our next step is we need to now compute the limit of this function, 3xy squared over x squared plus y to the fourth, as xy goes to the origin. So we need to investigate the limit as we approach the origin of the function 3xy squared over x squared plus y to the fourth. Why just this function? Why not the whole thing? Well, remember, we're approaching the origin along any path, and any path to the origin necessarily does not also, all the points except one are not at the origin. They're in the domain of this part of the function. So this is this is the function values along any path to the origin. So we need to investigate this limit. It looks like there's nothing that's gonna like cancel off immediately, and so that kind of tells me, oh, maybe I should be looking and seeing if maybe the limit doesn't exist. It's sort of looking like the limit might not exist here, and so then I want to consider families of paths that go through the origin. I could consider lines, I could consider parabolas, things like this, other such curves. Now for this one, I'm going to jump right to what the right answer is, and that is we should consider parabolas. That lines aren't actually going to work out. So maybe I'll do that at the end and show you that lines don't work out. But I'll sort of tell you parabolas work for this one. So we're going to try parabolic paths to the origin. And actually more so the idea here is I want some things to cancel when I consider these paths. And one thing I can see here is if I let x be, let's say x is y squared, then I'll have x squared, so that'll be y squared squared. That'll be y to the fourth. I'll get 2y to the fourth here. And if my x is y squared, I'll get 3y to the fourth here, and then I'll have some cancellation. So this is sort of how I get to force some cancellation to happen along certain paths. If I just pick lines, there's not going to be a lot to cancel here. So this is another way, sort of clue that I should consider parabolas rather than paths. And not just any parabolas, but parabolas that look like x equal y squared. So x equal, let's say x equal my squared for various values of m. So these are not just any old parabolas. These are sort of on their side if we're looking at the xy plane. So we're going to consider these guys. And let's go ahead and do that. So we're going to do limit as xy approaches 0, 0 along the parabola x equals my squared. All right, of the function 3xy squared over x squared plus y to the fourth. All right, well, if I'm going to the origin along this curve, then I want to send y to 0, and then x will go to 0, and my point will go to the origin. So I'm going to do limit as y goes to 0 of, now I'm going to substitute my squared for x. So that's 3 times my squared times y squared all over my squared squared plus y to the fourth. All right, let's simplify that a bit. Limit as y goes to 0 of, what do I have on top? I have 3m y to the fourth. On the bottom here, I have m squared y to the fourth plus y to the fourth, so that's m squared plus 1 y to the fourths. M squared plus 1 y to the fourth. All right, cool. The idea was that made my y to the fourths cancel out, and I'll just end up with a constant here, 3m over m squared plus 1. So constant with respect to x and y, but not necessarily with respect to m, right? As I change m, this value is going to change. So the idea is if I approach along the parabola, so along x equal y squared, we get, so that's when m is equal to 1. We get 3 over 2. We get 3 halves as the limit. And maybe if I approach along x equal negative y squared the other way, so set m equal to negative 1, we get negative 3 over 2. We get negative 3 halves. So that's 2 paths that go through the origin that give me different values for the limit. So since these are not the same, the limit does not exist. Hence, the function is not continuous. The function f is not continuous at the origin. Right? The limit doesn't exist at the origin. It'll exist everywhere else and be equal to the function's value at that point, except at the origin. So this is not continuous. All right, so what's going on here? What is going on here that's making this happen? I like to investigate the actual surface, the actual graph of this function, so we can see what's going on here. So I'll go ahead and jump to an interactive figure. Jump to, oh, do I have the right one queued up? Yep, there it is. There's my surface. So we can just graph my surface. Right, 3xy squared over x squared plus y to the fourth. And so here I have the blue curve is the function values along the parabola x equals y squared. Right, so there's x equals y squared. Right, should look familiar. And there's the function values, and it looks like my function values approach, what was it, 3 halves, 1.5 along that curve as we go to the origin. And then we also looked at negative 1, y equal, or x equal negative y squared, and we get negative 3 halves, because as we approach along those values, again, the blue is my actual function values along that curve. We're going along that part of the surface, which is below the zx, or below the xy plane, and we get out negative 3 halves. So this surface is pretty funky. Look at it. And this one, so certainly if we would have graphed this, these parabolas really stand out, and we would have been able to figure out, like, oh, maybe we should try parabolas, because this thing is looking pretty funky. So it's a cool one, and it's not continuous at 0, 0, even if we define the function to be 0 there. Again, because these limits did not match up. All right, that is it for this video. I'll see you next time.